Swayam Prabha. Digital India. Educated India.
Hello students, this is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University. We are discussing about periodic properties, which is a part of inorganic chemistry syllabus of our BSc semester 1 with BSc honors in chemistry as a course. And this lecture is being prepared under the academic expertise of Professor L.J. Paliwal. Now, in previous two lectures, we have discussed a few periodic properties like the atomic radius, ionization enthalpies, then the screening effect and the effective nuclear charge, electron gain enthalpy, etc. Now, we will continue with the remaining periodic property in this particular lecture. So outline of this lecture is discussion about electronegativity, the scales of electronegativity. Then we will discuss about variation of electronegativity in a periodic table. And in the end, we will see what is electron density ratio according to Sanderson concept. Let us start with what is meant by an electronegativity. Now we know that when a molecule is formed, or most of the times what we talk about is a covalent bonding type of bonding takes place between two atoms in order to pair up their electrons or unpaired electrons. Now, when this bond is formed, the electrons get paired up and the electron pair is normally present in between the two atoms, or the maximum probability of finding the electron pair is at the center of the two nuclei. This is what is expected when a bond is formed by equal sharing of electrons. This electron pair is under the influence of applied field by both of the nuclei. Hence, this electron pair is under the influence of the nuclear force of both the nuclei of the bonded atoms. The force of attraction of this electron pair and the nuclei is expressed in terms of electronegativity, and this word electronegativity is defined as the relative strength of the atoms to attract the shared pair of electrons, that is called as electronegativity. Now this is definitely different from the electron gain enthalpy. Electron gain enthalpy is an individual property of an atom where the electron is added to the isolated gaseous atom, whereas electronegativity is a term which is a relative term, and it is a relative force of the attraction between the bonded pair of electron and the nucleus, and this type of force is existing in the form of electronegativity, and this is present not in the atom but in a molecule where the two atoms are bonded with each other by covalent bonding. Consider that if you have two atoms and the nuclear force of attraction is equal in both the atoms, in that case, what will happen? This electron pair will be located exactly at the center, or in general what we can say is the probability of finding this electron pair is maximum at the center. This is similar to a simple example. We can say if we have two different partners, they are starting a business by sharing their capitals and getting the profit equally distributed among them when they get the profit. So the profit is getting equally distributed between both the partners. This will happen, or this is the ideal situation, when both the partners are equally powerful. Such situation arises whenever there are homonuclear diatomic molecules like H2, N2, O2, Cl2. In such cases, both the nuclear charges are equal and the force of attraction between the nucleus and the electron pair is equal, and hence in such case there is a symmetrical distribution of the electronic charge. And we can say that if you have two nuclei, the probability of finding the electrons follow this type of oval shape with maximum probability exactly at the center. This is the ideal situation followed in homonuclear diatomic molecule. But in case of heteronuclear diatomic molecules, the force of attraction between nucleus and the electrons is different. For example, if you have two different atoms, with one atom is exerting less force, whereas the second nucleus is exerting higher force or larger force on the bonded electron pair, then what will happen? This is a situation whenever you have an extra force on one side, there is a shifting of electron pair towards one of the bonded atoms. In this situation, we can say that the profit is unequally distributed. See, the capital is shared equally because both of them are sharing one electron each, but the profit is taken away to a greater extent by a person who is having larger power. So this is similar to this analogous example in our daily life. This is possible if the bonded atoms are heteronuclear diatomic molecule, or bonded atoms are having unequal forces of attraction towards the bonded electron pair. So many heteronuclear diatomic molecules like HF, HCl, etc. or polyatomic molecules like H2O, NH3, etc. they have this type of unequal distribution of forces, and it results in the shifting of the bonded electron pair towards one of the bonded atoms. And we can express this type of shifting in terms of the probability distribution curve or probability distribution of the electron. We can see that this hydrogen is less electronegative, chlorine is more electronegative. As a result, the electron charge cloud or electron cloud is more centralized on chlorine as compared to hydrogen. So the electron density gets shifted towards chlorine atom. Now what are the factors which govern electronegativity? The first factor which governs electronegativity is the nuclear charge, and second factor which governs the electronegativity is atomic size. We will discuss both of them in detail. The first factor governing electronegativity is the nuclear charge. Consider two atoms having equal size but different nuclear charges. So this atom is having higher nuclear charge, this is having a lower nuclear charge. And since this is having a higher nuclear charge, it will have a greater tendency to attract the shared pair of electron towards itself. As a result, this electron pair will be slightly shifted towards this particular atom. Hence, the electron density will be populated to a greater extent on this atom having higher nuclear charge, and the electron density will be lower on the other side with lower nuclear charge. In other words, we can say that the electronegativity is directly proportional to nuclear charge on an atom. Second factor is the atomic size. Consider two atoms having equal nuclear charge but different atomic sizes. So one atom is having smaller size, second atom is having larger size. Now if we know that the force of attraction between two charges or two opposite charges is inversely proportional to distance between them, hence we can say that the force of attraction between this particular nucleus and the electron pair will be larger. As a result, this electron pair will be slightly shifted towards this nucleus. Hence, the electron charge density will be higher on this atom as compared to this atom. Hence, we can say in short that the atomic size has an inverse effect on the electronegativity, or the electronegativity is inversely proportional to atomic size. Smaller size will have higher electronegativity and larger atomic size will lead to lower electronegativity. Let us see how the electronegativity varies in a periodic table across period and down the group. Now when we move across the period from left to right in a periodic table, there are certain variations which take place. The first variation is we know that the nuclear charge goes on increasing because the atomic number goes on increasing from left to right. And we know that the electronegativity is directly proportional to nuclear charge. It means that from left to right, nuclear charge is increasing and so electronegativity should go on increasing. The second factor which goes on varying from left to right is the atomic size. The atomic size goes on decreasing from left to right in a periodic table. This we have already discussed in previous lectures. This is due to increase in the effective nuclear charge, and hence we can summarize that since electronegativity is inversely proportional to atomic size, the net effect of both of these factors will be continuous increase in the electronegativity from left to right in a periodic table. So electronegativity goes on increasing from left to right. Consider the example of second period element. When we move from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, what is the trend of electronegativity? We can see that there is a continuous increase from lithium to fluorine, and neon is having zero electronegativity due to its noble gas configuration and completely filled valence shell. So there is no anomaly from lithium to fluorine with a continuous increase in the electronegativity from left to right across the period. Now when we move down the group, what happens to electronegativity? Again the two factors, the effect on the two factors if we consider, we can automatically come to the conclusion of variation of electronegativity. The first factor is the nuclear charge. Now whether we are moving from left to right in a period or we are moving down the group across or down the group from first period to second period, third period to fourth period and so on, in both the cases the nuclear charge always goes on increasing due to increase in atomic number. Hence it is expected that electronegativity should go on increasing. But the atomic size also goes on increasing when we move down the group. And we know that atomic size has an inverse effect on electronegativity. It means that these two are contradicting each other down the group. Among them, the stronger one is the increase in the atomic size from first period to seventh period. So when we move down the group, the atomic size increases substantially. As a result, this supersedes the effect of nuclear charge, and as a result, when we move down the group, there is decrease in the electronegativity due to increase in the atomic size. In other words, or in short, we can say that electronegativity goes on decreasing down the group. Consider an example of first group elements moving from hydrogen to lithium to sodium to potassium to rubidium to cesium. We will find, or we can find, the slow decrease in the electronegativity from 2.1 in hydrogen to 0.7 in cesium. This is a continuous decrease without any anomaly. In short, we can summarize the effect of all the factors together across the period. We can see that the electronegativity goes on increasing, and down the group the electronegativity goes on decreasing. The effect of this is the most electronegative element lies on the top right corner of the periodic table, which is fluorine, and the element with lowest electronegativity lies on the left bottom of the periodic table, which is cesium, leaving behind the francium and all the radioactive elements and a noble gas on this side. These are the two elements which show extreme electronegativity values. This is a trend of electronegativity with respect to atomic number. We can see that after hydrogen, we can go from for helium, it is coming out to be 0. Then all the noble gases have 0 electronegativity, and the electronegativity goes on increasing across the period up to halogen element. And these are the halogen elements having highest electronegativity values in each period. Now let us discuss the scales of electronegativity. Now this is an interesting point. Till now, whatever periodic properties we have discussed, we never discussed about the scales because all of them were the absolute properties. For example, it is ionization potential or atomic radius or electron gain enthalpy. They are the absolute properties of the element itself. But when it comes to electronegativity, it is a relative property of the two elements which are bound by a covalent bond. Hence, different scales have been proposed for the relative strengths of these electronegativities. The electronegativity is a relative tendency, and hence the calculation of absolute value of electronegativity is very difficult. Because of this, various workers have given different methods for calculating the values of electronegativity, and we will discuss the work of each and every person and contribution in calculating the electronegativity values. The first scale is the Pauling scale suggested by Linus Pauling in 1932. According to Linus Pauling, if we consider two molecules, like A2 is a molecule which is a homonuclear diatomic molecule consisting of two A atoms. Another molecule is a B2 molecule which is again a homonuclear diatomic molecule consisting of two B atoms, and a third molecule which is a AB molecule consisting of one A atom and one B atom, which is a heteronuclear diatomic molecule. And if the bond energies of A2, B2 and AB molecules are EAA, that is bond energy between A and A atoms, EBB, that is bond energy between BB atoms, and EAB is the bond energy between A and B atom. Now, Pauling defined a value delta or delta E, that is the difference in the energies, that is the energy or bond energy of AB molecule minus the geometric mean of the bond energies of A2 and B2 molecule. Now, EAA is the bond energy of A2, EBB is the bond energy of B2 molecule, and difference between these two values is defined as delta, or sometimes also shown by symbol delta E. According to Pauling scale, the electronegativity difference between the two atoms, that is denoted by a symbol chi A minus chi B, the electronegativity difference is proportional to this delta value. Larger is the difference between these two, the geometric mean of the bond energies of the homonuclear diatomic molecules and the bond energy of the heteronuclear diatomic molecule. The difference between the two is directly proportional to difference between the electronegativities, and this is given by chi A minus chi B is equal to 0.208 under root of delta. This is what is called as Pauling scale of electronegativity. These are the chi A and chi B are the symbols, or chi is a symbol used for electronegativity, and delta here in this case is actually the bond energy difference, and hence it is expressed in kilocalories per mole in this particular equation. But if the delta is expressed in kilojoule per mole, then the value, the constant value on this side changes to 0.1017 under root of delta, and the unit of delta here is kilojoule per mole, which is a SI unit. So both of these can be used as Pauling scales of electronegativities, and you can see that what we get in Pauling scale is the difference in the electronegativities of the two. Second scale is the Mulligan scale. According to Mulligan, the electronegativity is nothing but the arithmetic mean of first ionization enthalpy and first electron gain enthalpy or electron affinity of an atom. That is, according to Mulligan scale, electronegativity is equal to ionization enthalpy plus electron affinity divided by 2. If we take these two or the arithmetic mean, in that case, the values of I and E are expressed in electron volts. Now, if these values are obtained from Mulligan scale, it was found that the values obtained by this equation are 2.8 times higher than those obtained by Pauling scale. Hence, in order to match the two scales, a correction factor of 2.8 was applied and according to Mulligan scale, the electronegativity was put as I plus E, that is ionization enthalpy plus electron affinity, divided by 2 into 2.8. Now, if these values are put in electron volts, I and E values, and the values are put over here, then the Mulligan scale almost matches with the Pauling scale. This gives a uniformity. But if we want to convert the values of I and E in kilojoule per mole, then the equation of electronegativity becomes I plus E divided by 2 into 2.8 into 96.48. It is a correction factor, or what we can say is the conversion factor of values of I and E used in electron volts to kilojoule per mole. And hence the value of electronegativity comes out to be I plus E divided by 540, and on that scale we know that the Mulligan scale and Pauling scale, they match with each other with this correction. The third scale of electronegativity is Allred-Rocho scale, put forward by Allred-Rocho in 1958. According to these two scientists, the electronegativity is nothing but the nuclear force experienced by an electron present on the surface of the atom, that is the valence electron. So according to them, electronegativity is the nuclear force experienced by the valence electron. Now, we know that the force of attraction between two different charges is equal to Z effective divided by R square. It is the force experienced by the electron, and Z effective is the effective nuclear charge which is experienced by the electron, and R is the distance between the nucleus and the outermost electron, that is the radius of an atom. Now, this force was correlated with Pauling scale and corresponding correction was applied, as according to Allred-Rocho scale, the value of electronegativity chi is equal to 0.359 Z effective upon R square plus 0.744. When these values were calculated, they were found to be in close proximity with the Pauling scale values. The fourth scale of electronegativity is Mulligan Jaffe's scale. According to Mulligan Jaffe scale, when the ionization energies and electron affinities of atom are plotted against the oxidation state, a smooth curve results, and total energy can be described by a quadratic formula. The quadratic formula is given by E is equal to alpha Q plus beta Q square, where E is the total energy associated with the atom and Q is the ionic charge. Alpha and beta are the constants. This is related to the oxidation state. Q is the ionic charge, is the oxidation state of an atom. According to Mulligan Jaffe scale, the electronegativity of any atom is given by, this is chi m, that is the value of electronegativity on Mulligan Jaffe scale is equal to del E by del Q, that is partial differentiation of this total energy with respect to the charge on the ion, or that is equal to alpha plus 2 times beta into q, taking derivative of this, partial differentiation of this. So this is the scale used by Mulligan and Jaffe. Now this scale is applicable whenever there is a charge on the atom, that is in different oxidation states we can calculate the value of chi m. For example, we can calculate the value of electronegativity of an atom like say Fe atom, then Fe2 plus ion, Fe3 plus ion, and so on. The last scale of electronegativity is the Sanderson's electron density ratio. This is entirely different type of visualization. According to Sanderson, the electronegativity is related to relative electron charge density. And so chi Sanderson, that is the electronegativity on Sanderson scale, is equal to the stability ratio. And this stability ratio is given by d upon di, where d is the electron charge density given by 3z upon 4 pi r cube. Z is the nuclear charge and r is the radius of an atom, or in other words it is the difference between or the distance between the nucleus and the outermost electron. This is the value of density of a particular atom, whereas di is the electron density of isoelectric inert atom, that is the atom having same number of electron but which is a inert atom. This is all about the various scales of electronegativity put forward by various scientists. Now let us see what are the effects of bond parameters on electronegativity. The first effect is of hybridization or bond order. Now we know that s orbitals are more penetrating towards the nucleus. We have discussed this effect of penetration while discussing the ionization enthalpy values. We know that s orbital is more penetrating than p, which is more penetrating than d, which is more penetrating than f orbitals. This we discussed while discussing the distribution of electron charge density in various orbitals. Now, more is the s character in a particular orbital, more will be the nuclear force of attraction, because s orbital has got higher probability of finding near the nucleus. And hence, we know that sp3 hybridization has 25% s character and 75% p character, because it is formed by one s orbital and 3 p orbitals. Similarly, sp2 hybridization has 33% s character and 66% p character, and sp hybridization has 50% s character and 50% p character. So if we see these three hybridizations, we can find that sp hybridization has highest percentage s character. In other words, sp orbital is more penetrating towards the nucleus, and as a result the carbon atom shows different electronegativities in different compounds. This is an example. This is applicable to all the other atoms also. For example, if we consider carbon atom, we will find that the electronegativity of carbon is different in CH3CH3, that is alkane or ethane, than ethylene, than acetylene. Now in this case the hybridization is sp3, in this case it is sp2, and in this case the carbon atom is sp hybridized, and hence the electronegativity of carbon is highest in case of sp hybridized carbon in acetylene. So electronegativity is not only governed by the other atoms which are present, but also by the percentage s character in different hybridizations. So we can correlate electronegativity with bond order also. We can see that if in case of single bond, the electronegativity will be lower. In case of triple bond, it will be highest. Second parameter is the group electronegativities. Now we know that organic functional groups have a combined effect on the bonded electron pair, and hence effect of such group is defined as the group electronegativity, and this electronegativity is due to resultant of inductive effect and resonance effect of the entire group and not of an individual atom. For example, if we consider the carbonyl group or cyanide group or nitro group, now they have got electron withdrawing effect, while OH and NH2 group have electron releasing nature. Now it means that if you have any atom bonded with carbonyl group or cyano group or NO2 group, in this case the entire group will behave as a single entity and it will pull the electron pair. So it is the group electronegativity which is considered in such case. Similarly, in case of OH and NH2 group, it is electron releasing. So whatever is the other group or atom which is bonded to such groups will be attracting the electron pairs and will show larger electronegativity. The third parameter is the electronegativity and bond polarity. Now, if the difference between the electronegativity of bonded atoms is very small, the electron density is evenly distributed and a bond is nonpolar. Whereas, if the electronegativities of the two bonded atoms, they differ or they go on differing by larger values, the bond polarity goes on increasing, and if the electronegativity difference between the bonded atom becomes larger or much larger, then bond becomes ionic. Quantitatively speaking, if the electronegativity difference between the bonded atoms is less than 0.4, then we call the bond as a pure covalent bond. If the electronegativity difference is between 0.4 and 1.8, we call the bond as a polar covalent bond because there is a polarity induced and the electron charge density is unevenly distributed. Whereas if the electronegativity difference further increases to more than 1.8, we call the bond as a ionic type of bond. So electronegativity governs the bond polarity also. This is all about this particular lecture. We will continue with this topic in our last lecture of this module, that is lecture number 4. Thank you very much.